Welcome! In this video you will learn about the concept of a subspace, also called a linear subspace. Linear subspaces are subsets of Rn with certain special properties. As we will see, these sets arise in a natural way in linear algebra. Let's start by looking at an example. Consider the solutions of the homogeneous matrix equation indicated on the slide. Let's call the solution set H. As you can check, for this equation, the solution set H can be visualized as a plane in R3 through the origin. Let's look at some properties of this set. First of all, we know that the zero vector must be a solution of the equation, so the zero vector is contained in H. Furthermore, consider the solutions 1, 1, minus 2 and 1, minus 2, 2. Note that the sum is also a solution, hence contained in H. This is just an example of a more general property. If V and W are vectors in the solution set, then the sum V plus W is also in H. You can show this using the rules of calculations of matrix vector multiplication. Geometrically, it means that we cannot get out of H by adding vectors. We say that H is closed under vector addition. Finally, look again at the solution 1, 1, minus 2. 2 times this vector is again a solution, and again this holds more generally. If V is a vector in the solution set and C is some scalar, then C times V is again a solution and therefore contained in H. We say that H is also closed under scalar multiplication. These three properties are exactly what makes H into a linear subspace. Let me give you the precise definition. A set H in Rn is called a linear subspace if it satisfies the following requirement. H contains the zero vector. If you take two vectors in H, the sum is still in H. And if you take a vector in H and multiply it by any scalar, then the result is again in H. Note that it follows from this definition that any linear combination of vectors in a linear subspace is again contained in that linear subspace. You cannot get out of the subspace by taking linear combinations. Another way to say this is that linear subspaces are closed under taking linear combinations. These three properties severely restrict what a linear subspace may look like. For example, look at the first quadrant in the plane. Is it a linear subspace? Well, it contains the origin, so it satisfies the first requirement. And if you add two vectors in the first quadrant, the result is still in the first quadrant. So also the second property is satisfied. Now take a non-zero vector in this set. If you multiply it by a positive scalar, like 2, it is still in the set. But if you multiply it by a negative scalar, like minus 2, the result will not be in the first quadrant anymore. Therefore, the third requirement is not satisfied, so this is not a linear subspace. Okay, but what can a linear subspace look like? Let's look at subspaces of the plane. The smallest possible linear subspace is the set containing only the zero vector, the origin. Indeed, if we multiply the zero vector by a scalar, we simply get the zero vector back. And if we add it to itself, we still only get the zero vector. We cannot get out of this set by taking linear combinations. Let's try to make the linear subspace bigger by adding a non-zero vector V. Then it automatically contains all scalar multiples of V. That is, the line spanned by this vector. On the other hand, this line itself is a linear subspace. Try to check it yourself. In fact, every line through the origin is a linear subspace of R2. Let's try to make this linear subspace even larger by adding a vector W that's not on the line. Since the subspace has to contain all linear combinations of V and W, you see that in fact it has to contain all vectors in R2. Of course, R2 contains the origin and is closed under vector addition and scalar multiplication, so R2 is a linear subspace of itself. It is the largest possible linear subspace of R2. Let me end by stressing the big idea of linear subspaces. Within a linear subspace, you can add and scalar multiply vectors just as you can in Rn. This means that everything in linear algebra that we did on Rn, you can also do within a linear subspace. You can make this connection between subspace and Rn precise by using the concept of a basis. You will learn more about that in class.